Okay, so my name is Sanpera. I am a professor at the University Autonoma of Barcelona, an INQA professor. I'm also in the group of quantum information, which is, here, group of quantum information, and well, I have to acknowledge also Quantum Spain and Women for Quantum, which is an organization that we are leading, which aims to increase the number of women, which is very small, as I can see in this situation. So let me show first the team that I'm going to present today. So this is part of our, we are over 25 people, and this is the team I'm going to present today working on this problem. So we withdraw Guillem Abad from Kilimanjaro, and now he's with us. So this is 1-0 for the JIC. Hari Krishna, which is doing the PhD with us, Ayaka Usui, which is doing a postdoc with my group, and also Soma Bhattacharya, which is also doing a postdoc. And we also have a postdoc from another algorithmia that is coming to us, so which is also 2-0. Okay, it's very difficult now to get people from the industry. So. I'm a little bit tangential from this quantum annealing, but I work quite a lot in this quantum simulation, and I wanted to give an overview of how we see this problem a little bit before talking about the specific point. So there is some facts, no, that most of you know that local Hamiltonians are the workhorses of many body physics. Many body physics has a lot of consequences, quantum materials, whatever you want to say, okay? And that many body physics is notoriously difficult, okay, to calculate even, which is because many problems, not only because the Hilbert space is very big, but also because it's very difficult to embed these things in simulations, the dynamics is super complex and so on. And so there is some questions that we have been addressing in these last couple of years, 3 years. One, it's more theoretically, it's like, okay, what is the manifold of local Hamiltonians? What is this thing, all right? So normally people talk about Ising Hamiltonians, and then you say universal Hamiltonians, but there are many Hamiltonians in the world, and although we will explain a little bit how do you go to that. Then there is another question that we have been interested on, which is a very typical question, which is, okay, if you give me a Hamiltonian, I want to infer which is the operator content of this Hamiltonian, and also from incomplete data, okay? So what does it mean? So for instance, you have an experiment, analogic, digital, you get some data because you don't have access to everything, and you don't know the Hamiltonian. Typical paradigmatic, well-known example is high TC superconductivity. Okay, so you have a lot of data about high TC superconductivity. Everybody will like to prepare and say exactly which is this Hamiltonian, because the consequences of high TC superconductivity are huge because you don't have resistance to electric flow, so that will be, but the Hamiltonian, it's not known, okay? So you will like to do that. This is normally what people call Hamiltonian learning. But also, we were interested, and we have been working in another problem, question 3, how do you simulate a complex Hamiltonian with a simpler one, okay? Because maybe you have a Hamiltonian which is very complex, but I want to go to an experimentalist and say, oh, the physics is very important. This is the dual question. This is more or less what we call a quantum simulator. So you have a platform, experimental platform, can be analogic, can be digital, and you would like to implement Hamiltonian in a way that you can implement it in the lab that describes a physics that you cannot solve in a classical computer. And this is the goal of quantum simulators as such. And then there is another question, which is the one that I would like to talk today about, which is this Q4, question 4, how to simulate local Hamiltonian dynamics. Okay? But before going to that, let me just, this is also the ABC of local Hamiltonian. So interacting quantum systems are local Hamiltonians. And so we defined it like that. Given n parties, each party of dimension d doesn't need to be the same dimensions, but normally this is the case. You can write that your Hamiltonian H lives, okay, in a Hilbert space, which is the tensor product of all individual parties Hamiltonians, okay? And then you describe a Hamiltonian, you say, okay, my Hamiltonian, HK, it's K local, okay? If I can write it as the sum from I to M of smaller Hamiltonians, HI, where HI is an n-body Hamiltonian that has at most K interactions. And this is how we defined a local Hamiltonian. Okay, typical examples are the ones that we have seen already this morning, Ising spin model. So I have the Ising sigma x, okay, two local Hamiltonian plus a magnetic field, one local. So this is a two local Hamiltonian, but there are other Hamiltonians which are not two local and which are very interesting. Kitaev toric code, lattice gauge theory, in which you have to have at least a lattice. So a lattice means that you have to have a plaquette which is at least 3-body or 4-body, because you have to have a magnetic field going through this plaquette. And you can ask, okay, simulating in a lab a 4-body Hamiltonian or 5-body Hamiltonian is probably very difficult, if possible. Can we give a recipe to say, okay, part of the physics, you can do it with a 2-body Hamiltonian? Okay, and this is the work. The first one, I will just say the first one thing. So this is work that I have been doing also with Maria García Díaz, which is at the University Polytechnic of Madrid, and at some moment she was a postdoc with us. So we decided to reframe this problem of how is the manifold of local Hamiltonians from the things that we know from quantum information, because these things are very similar. Okay, so you have a Hamiltonian which is a bounded operator, so we will assume that we have Hamiltonians that the maximum energy is bounded, it's not infinite, and this is most of the local Hamiltonians, not to say all the local Hamiltonians are bounded. The Hamiltonian doesn't need to be a positive operator, because obviously if you measure the energy, it can be negative, but it doesn't matter because you add the identity to this Hamiltonian and it becomes positive. And when you add the identity, you don't change neither the eigenvectors, they are the same, so you don't change the Hamiltonian, and you just shift all the eigenvalues, but you don't change the spectrum. So therefore, these two Hamiltonians are identical and they are trace one. So this, for the people who work in quantum information, this is a density, this describes a density quantum state in a mixed state. Okay, so, and it works like it works for the mixed state. So the local Hamiltonian, it's a k-nested structure, and it's very simple. So you have Hamiltonians which are like that, one local. In other words, they are Hamiltonian that they don't have any interaction. Okay, so a Hamiltonian which is a magnetic field sigma z. Okay, so you cannot create from a state which is entangled any entanglement with one local Hamiltonian. Then you have two local Hamiltonians, and this is more or less what everybody studies, because this is the typical thing that happens in nature, that interactions are two bodies. So this is the manifold of two local Hamiltonians, and of course one local Hamiltonian and close to two local, and so on. And then n local Hamiltonian, and then you have the Hamiltonians that they are not local. Not all the Hamiltonians are local. Okay, and then you ask yourself some questions. So you can say, okay, if I have a Hamiltonian maybe which is two local, can I approximate it? So how far it is from one local? Because in some way, this has to be related with the amount of entanglement of the eigenstates this Hamiltonian has. So then you can also ask these questions, that if you have Hamiltonians that you know that all the eigenstates of these Hamiltonians are very little entangled, typical thing, area low Hamiltonians, we ask, are these area low Hamiltonians that they present very low entanglement close to the one local, and so on and so forth. Okay, so this is the first question. Second question, how to infer the operator content of a Hamiltonian from incomplete data. Well, this is the typical question that you have a parent Hamiltonian, let's say, which has some operators. I put here two-body, but it doesn't matter. EA, BJ, and you don't know what it's AB, AI and BJ, and you don't know neither which is the coupling. And what do you want to do? It's you have some measures, this is what I was saying, and from data, some data, which this data can be experimental data, but can also be theoretical data. No? So for instance, I give you an eigenstate of a Hamiltonian, and I say, I only know that, which is the parent Hamiltonian that has this state as an eigenstate, okay? So this can be also a theoretical question, and you say, I want to know. Of course, how many Hamiltonians have the same eigenstate? Infinite many. But if you put correlations, you say, how many Hamiltonians that they are two local have this eigenstate as a ground state? Well, this then the question starts to restrict. So this is what it's normally called in this field quantum Hamiltonian learning. And the opposite, okay, it's given a Hamiltonian and I produce some data, okay, this is what a quantum simulator does. Maybe I don't know exactly the Hamiltonian, but I produce data. So these two problems, in some way, one can understand them as one dual of the other, okay? Quantum Hamiltonian learning wants to learn which is the parent Hamiltonian from a data. Quantum simulator puts a Hamiltonian and produces that data, okay? So So, and there are, of course, as you can imagine, very interesting problems that I'm not going to talk about that, but something a little bit similar. The third problem that we have been working a little bit, it's how can I simulate a complex Hamiltonian with a simpler one, okay? And so formally, the problem, I can put it like that. Given a target Hamiltonian, or parent Hamiltonian, as you wanted to say, HT, which is k-local, can I find a quantum simulator Hamiltonian, which is k-prime local with k-prime smaller than k? And this problem which means is the following. No? Imagine that I give you a Hamiltonian, a parent Hamiltonian, a target Hamiltonian that I know it's k-local, I don't know, lattice gauge theory, super complex, and I say, no, listen, I cannot go to Leticia, which is not here, but she will talk this afternoon about quantum simulators, to simulate that, because this is 5 local, or 3 local, or 4 local, but maybe she can do a 2 local. So, and I want to provide her this 2 local Hamiltonian that approximates this other Hamiltonian. And of course, when we want to do that, we have to know what doesn't mean approximate and what is the thing that we can approximate. Remember that a Hamiltonian is unique, okay? So, 2 Hamiltonians that they have the same spectrum and the same eigenvectors are the same Hamiltonian. Okay, so these things, okay, go, and somebody was talking this morning about the concept of universal Hamiltonians, which is a super interesting question. I'm going just to give a very intuitive flavor of what does it mean a universal Hamiltonian. I told you that 2 Hamiltonians, they cannot have the same spectrum, okay, eigenvalues, and the same eigenvectors. Right? If not, they would be the same. But obviously, it can be that if I have my target Hamiltonian, that it has this thing, can I engineer a quantum simulator Hamiltonian that reproduces this part, okay? And the answer is yes, and it's super interesting. You can do it, and you can do it with what it's called universal Hamiltonians, okay? So there are certain 1D translational invariant 2 local Hamiltonians that they are universal, okay? Which is the price that you have to pay? Well, the price that you have to pay is that you have 2 prices to pay, okay? One is that a priori the dimension of the quantum simulator, this universal Hamiltonian, has to be much, much, much larger than the one of the target Hamiltonian. So this is one price. And the second price is that if you want to reproduce properly the interactions that define this small, my target Hamiltonian, the interactions, they have to be known with a precision that they are out of the experimental available nowadays, 10 orders of magnitude, 20 orders of magnitude. Okay, so this is the price to pay. This is a very interesting work, well, I mean, for me, from the group of Toby Kuwit and Dorit Aranov. Okay, so now I come to what I want to talk today, which is quantum Hamiltonian dynamics learning. And the problem that now we want to talk is a little bit different. So you have many problems that you can address on that. So for instance, I can say, do you want to know everything of a Hamiltonian? Well, probably not. Probably you want to know the low energy physics. So if you want to know ground state properties, you are interested in the low energy physics, maybe the ground state. Okay, this is the lowest energy physics, but physics doesn't happen at t equals 0, so maybe you want to know the ground state and 2 or 3 eigenstates. Maybe this is enough. This is one question that you can have. But if you do dynamics normally, okay, so you are at temperature different from 0, okay, and this is what it happens. Or you want to study dynamics, okay, you have to know more states. And this is what we have been working, or we are working now on that, okay? So what does it mean quantum Hamiltonian dynamics learning? Well, it means something very simple that we all know. So I have a state, psi 0. There is a Hamiltonian, okay? And I want to see the unitary evolution that comes from this Hamiltonian. So I have my unitary evolution, where the unitary evolution is the exponential of E minus ht. And I want to see what it's this. And I can observe which is this state psi of t. And in front of that, you can make also several questions. No? The first question is that, well, imagine that what I'm asking here is, I have a black box unitary, so I don't know what is in this box. So I know which is the initial state that I send, I know which is the final state that I get, and then I ask you, okay, can you tell me what is inside of this black box? This is obviously unitary Hamiltonian learning, and you can call it Hamiltonian learning, but these two things, they are not the same. So if you know the Hamiltonian, you know the unitary, but you can know the unitary without having exactly the same Hamiltonian. And this is why I like to call it Hamiltonian dynamics or unitary dynamics. So this is an example. But you can have other examples. So for instance, you can say that I want to do, so I know maybe that my Hamiltonian, it's a very complex Hamiltonian, for instance, 3-body Hamiltonian, okay? And I say, yes, I want to do a many-body unitary approximation. So I want to give you a unitary, which reproduces the same unitary, so the same dynamics of my system, but with a much simpler Hamiltonian, okay? And now I'm only interested in the dynamics. So it's very similar to the problem that we were doing that. And this is more or less the things that we are considering nowadays, okay? So, and in particularly this one, and I will explain you. But this is the framework that I want to say. So I can even have no idea about what is the unitary, and I want to know the unitary, or I can say, well, I know that I have a Hamiltonian that is super complex, okay? And I want to say, I want to reproduce the same dynamics with a much simpler Hamiltonian. How do I do it, okay? So let's see how it's the dynamics. So normally, when you want to do dynamics, and it was today even in the first talk, so you can do two things. Well, you can do many things, but these are the standard things. So I have my initial state, and I have my final state, so I measure my final state, and I do quantum state tomography, okay? So I'm measuring my final state, and knowing the initial state, I try to reproduce these black box dynamics. Okay, so, and I do it from different states, and then I characterize my dynamics, my unitary. And if I do that, the most efficient method requires of the order of d squared, where d is the dimension of the system. And of course, if I send an initial state, which is n-body, it's already pretty bad, okay? And there is also another way to do it. It's that if I have my unitary, and I can think that the unitary, I can chop it in small pieces. So this is the Trotter thing. So I can do this Suzuki-Trotter method, okay, and approximate that using quantum gates. And it has some things, but the Hamiltonian initially, so my black box, it should be known. And then I can say, well, I can simulate the dynamics using Suzuki-Trotter approximation. I have some errors because it requires well, first of all, I have errors if my Hamiltonian, when I write it as a local Hamiltonian, the terms of the local Hamiltonian doesn't commute. Of course, I accumulate errors, and it requires a large number of gates to implement the unitary Hamiltonian like that. Okay, but this is a very typical way to do it. Okay, so for instance, well, and with these two things, what I wanted to talk today, it's quantum machine protocol. I don't know, I don't work in quantum machine, okay? But I think this is inside of quantum machine protocols, which is called quantum generative adversarial networks, QGANs, that can overcome these limitations. And I want to explain how, and I want to explain what we think. This is not our contribution, what is our contribution to this field. And as a kind of example, okay, so if I have a Hamiltonian, which 3 qubits Heisenberg, okay, and I want to fix a time evolution, there is this paper by Chakrabarty et al., in which they show that if I use Trotter, I need of the order of 10 to the 4 gates, and if I use QGANs, I can approximate that by 52 qubits, gates. Okay, so this is a very different thing. So what is this QGANs? Okay, so I don't know if you are familiar. I was not familiar some time ago, so I like to start everything from the very scratch. So QGANs, it's adversary, you know? It's a game where you have to have an adversary, and it has 3 main components, and then you will see it's very close to the things that we want to do. So we have a state, we have a target, now it's a black box, okay? Either in the case that we don't know the unitary, or we want to simplify the unitary, so we put everything like a black box, and after my state goes to this target, it becomes psi t of the target, and now I have here a generator, okay? I will explain what is the generator. It's a quantum circuit. in which I put psi 0, and then I have psi g, the state after the generator. And here, which is very important, I have a discriminator. And the discriminator wants to discriminate between both of them, so maximizes the distance, looks at distance which is good and says, okay, psi t and psi g are very different, okay, and then the generator, okay, feedback receives this input and modifies his states, okay, on the thing, and again, you send another state, you look, so on and so forth, until if you have a generator, and then how is the generator? The generator has a series of layers inside, which is 1 qubit and 2 qubit, and if the number of layers is infinite, you reach Nash equilibrium, and you can find that the generator is equal to the target, so the discriminator say, no way, okay, I cannot distinguish, they are identical. But of course, you will like to do that without an infinite number of targets, okay? So in more graphical way, okay, so this is the target, this is the generator, okay? So our generator is parameterized, it's a circuit, so by some angles, okay, to approximate the unitary of the target. And the gates that they are in the generator have nothing to do with the target, because our target is a black box a priori. And the discriminator tries to distinguish between the target and the discriminator. Okay? So in order to do that, like in all these things, this is a min-max problem, no? So you want to maximize the distance, okay? This is the discriminator, minimize the overlap between the target generation and the generator generation, okay? And then you have to choose a function in order to do that, a cost function, okay? You have to choose it properly, and you say, okay, you want to look, okay? So maximize over the discriminator. So discriminator has also, it's whatever, it can be a measurement, it can be, you can change, okay? The distance between the generator, okay? So minimize over this thing so that the generator gets close to psi t. And you can put it in a more formal way in this way, no? So you have a random set of parameters for the generator and the discriminator, okay? Then you prepare your states to be compared, the one that comes from the generator, the one that comes from the target, and now you update the discriminator with your loss function, update the generator after that, estimate the fidelity between all of them, and return, okay? Again, until you reach your goal. And so the learning process, okay, it's tracked by a fidelity between the generator and the target, and you will say that you have succeeded, so you know the unitary that reproduces. So now I can go and say, okay, this generator reproduces exactly the unitary I wanted, okay? And with fidelity 1, you will finish. And again, this thing encompasses the two problems. Either my target is a black box, or my target I know. I want to know how I can simulate the dynamics of a 5-body local Hamiltonian with a 2-body local Hamiltonian, because the generator is always 1-body, 2-body. Okay, so in order to do that, of course, if I put here a target, okay, you will say, yes, maybe I will be able to find which is the good generator for this specific target. But this is not what we want, because we want to know the unitary, okay? So how do we overcome these things? Well, you can decide to send a lot of states here, okay? You decide to send several thousands of states different, and you do all these things, okay? But instead of doing that, you use something which is called CHOI, and you use the maximally entangled state. This is this contribution from Kim, Lloyd, and Marmion, that they were the ones that they were starting to do this Hamiltonian quantum Q-gangs. And what do? It's, okay, you have, of course, there is no free lunch, so you have to have a maximally entangled state. Part of these states passes through the target, part doesn't pass. Part of these states goes to the generator, and then in the discriminator you have all these things, and then again and again, and this is very easy to show. I have not put it here because I prepared that yesterday night, the things that you shouldn't do, but it's very easy to see that in this way the fidelity between, because you want here fidelity between gates, okay? So the fidelity, that means the trace of U dagger generator UT goes to 1, okay? Or it's better to go to 1. This is your goal, okay? To the two gates, they have to be equal, and then the fidelity is Hilbert-Schmidt. Okay, so what happens? Well, that life is complicated, and everything that you do that for any kind of thing, you always find that in most of the cases, you end up in a learning plateau. Okay, why? Because you have to minimize this max mix cost, or I don't know, for the people who is much more expert than me. So for me, it's understanding that this, you have a gradient, that there is a moment which is very small with a lot of parameters, and you get stuck there, okay? So it's the same as to saying you have, it's the same exactly as this talk in this morning. So you have an Ising model and you have spin glass, which means you have many locals, minima, and so on, so you don't know where you are. And this is the typical thing that it happens. So sometimes you start everything random, okay, and you look at the fidelity, and it increases, pam, and then you get in this plateau, okay? And I think this is a very nice paper, which the title says everything, okay? So it's like that. So every time that you try to do something, you get up. So, and now is where we start here, okay? How we can solve that, okay? So we can solve that saying that there is a possibility to go out of this plateau, which is to perturb the system, okay? I have to perturb the system because it is you are skiing, okay? And then suddenly everything is flat, okay? So there is no way, and you have to go to the village, but you have no idea where to go to the village. There is impossible, all right? So you need that somebody pushes you in the right direction. But you don't know which is the right direction, okay? But we know that if we do that, we can do it. So how do we look for the right direction? Well, the right direction, we do it in the following way, okay? So let's perturb our system by adding a supplementary system, an ancilla. So I'm talking to everything about qubits. I want to add a qubit, okay? And so I will do the following. My scheme, I will do, okay, I have my input state, which is this maximally entangled state, and in the generator, my input state, which is the same, and now I will add an ancilla. This ancilla in the target doesn't do anything, okay? But in the generator, this ancilla, I will put it through the generator. And then I will go to the discriminator, and I will have to look in this discriminator, okay, the distance. And of course, I have to put here the ancilla that doesn't do anything, because the discriminator has to look between something which is now with an ancilla, so the Hilbert space has increased by a factor 2, because I have put a qubit with something which has the same dimensions. So therefore, I have to pass it here, okay? And so now we look what it happens. And like everybody, I think, we are very modest because we don't know how to do it better, and we have a lot of restrictions. So we want to use Hamiltonian now, which is very simple, okay? But this is not the important thing. It's a three-body Hamiltonian. So my target Hamiltonian is a three-body Hamiltonian. I want to find a unitary with one-body and two-body gates, Hamiltonians, that reproduces this for any state that I put in my target, okay? So when we do that, okay, and I will put an ancilla, and this is what happens, okay? So when you do that, what happens? Of course, you have to do it everything statistical, because you start and your generator has random parameters, and then you repeat the changing the random parameters, and pam, 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 and then you run and you do, I don't know, I think these plots are average over 100 realizations, and this is the number of training, pam, 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 okay? And now we put an ancilla, okay? And then we see that we go to something much higher. It's not 1, but we increase, again, over a statistical average of all possible things. Okay, so when that happens, one asks why these things happen, okay? And let me look at that from a little bit more of a detail, okay? So what happens is that when I put in my target, I have this unitary of the target, and I put an ancilla that it doesn't interact. The Hilbert space, okay, and adding to ancilla is just a direct sum, okay, because I have a 0 and 1. So this is like how is the space in the unitary evolution of the target. While in the unitary evolution of the generator, that the ancilla goes inside, okay, I have increased also by a factor 2, But obviously, the generator, I cannot distinguish it like that. Okay, so it gets a huge a double space, Hilbert space. But at the end, the discriminator has to distinguish between these two guys. Okay, has to distinguish between these two guys. So what it does, well, it looks and distinguishes only on this part of here. Okay, so because the ancilla, it wants to take, if the ancilla that I put here, it's up, and the ancilla that I put here, when it goes out, it's a combination of up and down, it will project on the part which is up in order to get what is the unitary. Okay, so it does things. So the ancilla expands the interaction, so this is why it works, part of why it works. So the ancilla expands the space over which the generator is optimized, so opens new paths for optimization, but it's not only that. It mediates interaction between generator qubits through entanglement, and this is the important thing. At the end, this entangles, okay, the part of the training and only compares this first part. Okay, so it compares these two parts. So why it works? Well, and how it works. So now, well, why it works, I will tell you. Because you put an ancilla which is entangled with your state in the generator. So you can, at least this is how I imagine. So imagine that I am in this plateau, in this barren plateau, learning plateau. I have to minimize my function. Okay, so I start. Okay. And then there is a moment, and this is very important, that I arrive to this plateau, and now I put an ancilla, and I entangle this ancilla with my state in the generator, okay? And I kick everything. And this is like if you were thinking classically, like if you are really tidying all the qubits of your generator, okay, and looking for a new phase space. So the ancilla pulls all the other ones. Okay? And how do we know that happens? Well, we know that happens because that depends strongly on how do we put the ancilla. So here it's these 4 configurations that we look. So imagine this is a rotation of the ancilla, which is also random. So if the ancilla is only, and we have a 3-qubit simulators, if the ancilla is only entangled with one of the qubits, okay, or 2, the ancilla is entangled with 2 of the qubits, okay, but here we don't put this rotation, so it's always initialized in the same state, so this is the identity. Or 3, we do a rotation randomly when we put the ancilla and we entangle with these 2, or finally, okay, we do a rotation and then we entangle with all of them, okay? So this diagram of here shows that R is random rotation, so 1 qubit rotation of the ancilla, and every line it's a ZZ gate, like that. Okay, so let me show you the results, which are very simple. So, how it works, I told you when it works. So the ancilla cannot be added at the beginning. And the reason it's obvious, because if I add the ancilla at the beginning, okay, I have not reached a plateau. So I have to deanalyze and to do all this learning, and I will reach a plateau in another place, but I will reach it. So what I have to do is to put the ancilla when I reach the plateau, okay? Because this is the moment that they say, okay, you don't know how to minimize your gradient function, attach your qubits to an extra system, okay, and let them pull. And then you have to put it randomly, okay? It has to be random, so this is this rotation. So why again? Well, because every time that you reach a plateau, you are in a different number of states, in a different angles, in different, okay? So randomly, it's very important. So I put my ancilla, I do a rotation on the ancilla, and then I attach it. This is necessary, but it's not sufficient. What is necessary and sufficient is that the ancilla is entangled with all the generator qubits. So let me show you results that we have, which are very simple, because this is a simple model, and we are doing it now in more complicated things. So I look at this thing saying, okay, let's add the ancilla at the middle of the simulation, which is here, okay? This is the control, there's no ancilla, okay? This is putting the ancilla, and these are the different configurations, okay? A1, that means a rotation, but only entanglement with 1. A2, no rotation, so there is not randomization, even if there is entanglement with 2 or 3. A3, rotation and entanglement with 2 of them, and A4, rotation and entangle with all of them. Okay, so if there is not randomization, so this is the average fidelity in the plateau, and it remains the same, doesn't matter. But assume as you randomize, you see that the fidelity in these two places, it's very changes, but it's not too much change. But already when I am in these two topologies, okay, in which I have random parameters of the ancilla and entanglement with 2 or 3 of the qubits, the fidelity that I reach is much higher on average. Okay, so that means on average many times I reach 1, and on average sometimes I don't. But from 0.65 I go 10% higher, which we think it's really pretty good and pretty nice. What else? Okay, what happens? So when? Okay, when happens if we add this thing at the beginning? Well, if we add this thing at the beginning, the result is very insignificant. It even can decrease. And again, this is very logical, because if I don't have time to reach the plateau and I put an extra condition there, I will reach another plateau with the ancilla, okay? So we need to do something which is very typical in these problems: kick my system out and use entanglement to take it out of the system, okay? So I think that I am ready to finish. So this is what we have been doing. I mean, we have tried many things. Of course, there are other things that you can try. They don't work, I can tell you. So you can say, for instance, you say, okay, I have this problem, and at some moment I have many parameters to optimize, and when I reach a plateau, I'm going to change some of the parameters randomly. Well, that doesn't work, okay? So of course, if you change, because you have to choose which ones are good, which ones are bad, so in general, on average, that doesn't change. So what we have shown is this ancilla is able to kick the generator out of this learning plateau via entanglement. So this is really unitary learning through entanglement, assisted by entanglement. Configurations matter, okay? So we need, and we are working on that to understand theoretically why this is much better. Intuitively, it's very easy, that you have to pull all the qubits out of the plateau of the generator, and this is how you do it, okay? Being attached to all of them. So if you only can pull one of them, maybe you don't go out of the plateau. But this is, and also rotation, because this is randomly, and you know that randomness are very important in this process, that it's much better to add it in the middle run, so when you are close to the places where you find a plateau, and that when the gate parameters are initialized randomly, well, but this is typical thing, so that you have to put this random unitary there, okay? So from the ancilla every time. Things to do, many. There are many open questions. The first one, of course, you say, okay, what happens if you have a much more complicated Hamiltonian or more qubits? This is difficult for us to look at that, because when we put 3 qubits plus the ancilla, it's 4 qubits plus the target, it's 4 qubits. So we are already simulating with 8 qubits, 2 to the 8, it's our upper threshold, okay, on what we can do normally. So to go, we are now collaborating with other groups in order to increase a little bit these things, okay? Of course, we want to find an analytical expression why it works. We do theory, so we like to have analytical expressions why the entanglement has to be like that, if we can design the entanglement a priori. Well, we have to see how the performance they are, if we can increase, and many other questions that they are open still for research. So with that, I would like to finish. Thank you very much for your attention.
Do we have any questions? Yes. Okay.
Thanks for the talk. So what does the discriminator do exactly? Is it also a quantum circuit?
Quantum discriminator now is a quantum circuit, but it represents a measurement, if you want, that it has, okay, it has some parameters that you have also to optimize, because of course the discriminator is good when it's able to discriminate, so it has to be a very good discriminator.
So
now, as we do it, it's a quantum circuit.
okay, and so the fidelity is also a quantity that gives you the distance between them.
Yeah, but you have to choose a root.
Okay.
Because imagine that you do that with, let's say, 20 spins, okay? And you choose fidelity, typical fidelity, and you have that your generator reproduces 19 of these spins well at one value. That would be fidelity 0, and this is not a good measurement. So normally these things, we never use the fidelity. We call it fidelity, but we use a cost function that is much more similar to a Hamming distance, but it's Wasserstein distance. It's a cost function which is complex, but it tries to avoid this kind of easy zeros or plateaus, because just from 1,000 spins, one is different. Well, the fidelity has to be very high, but in the typical fidelity, that will be 0. It's not good.
Okay, okay. Thanks.
There's another question there, if you can pass the mic. Thanks.
Thank you. I would like to ask, so basically this is a trainability issue, right? It's not an expressivity issue. So when you reach the plateau, in principle, you would be able to obtain the target, but you cannot. So can you actually do some analytical or semi-analytical study on what happens to the optimization landscape if it becomes convex by adding the ancilla?
Yes, this is a super good question. This is what we are working, and as you say, this is a trade-off between expressibility of your generator, okay, and the plateau, and the learning plateau. So there is a trade-off, and this is what we are working. We are trying to find some analytical expressions to support that what we are finding. That is a super good question and very important.
Thank you.
Thank you for the question.
Thank you.
This one's closer.
Good morning. Thank you for the nice talk. I really appreciated what you described, also because you brought to the community also trainability issues like barren plateaus and these things that are that exist in quantum machine learning techniques. Just a very quick clarification. So maybe I'm wrong, but probably with your method that you described, and also there is a slide where you put the matrices where you described when you added the ancilla qubit, maybe you generalized or you reproduced actually what block encoding techniques does, where basically you create a block matrix. I mean, you find a unitary, exactly. So in the pink matrix, to the right, you basically found a map that basically creates a matrix into two blocks where you actually are interested only in the upper part of the matrix. This is the block encoding technique, probably, which helped. And another thing is that it's true that you have to carefully look at the expressibility of the circuit, but probably since you are working with a maximal entangling state, probably also the tangling capability probably is something which you should check. But it's very nice talk, and I really appreciated what you described. Thank you very much.
Thank you very much, because I'm honestly, I don't know very much. Okay, so these are the things that we are working because we are very interested. I think you are completely right, but there is a difference in the sense is that, so, but maybe I'm wrong. Okay? So
No, maybe I'm wrong.
very happy to discuss on this extra coding.
Yeah.
Because at the end, I say that happens, but that happens after the discriminator. Okay, so it's not that, because there are some schemes.
Right.
Yes, okay, and we are also trying that after this, and I think this is probably more close to what you say. Okay, so imagine that in this point of here, I measure. Okay, I measure
Yes.
my ancilla, and then, so to say, okay, by measurement. Okay, and now I say my ancilla here was spin up. Okay, a qubit in a spin up. And I measure here, and I only take the measurements that give me spin up.
Okay.
And then I think, maybe I'm wrong, that will be more similar to what you are saying, so that I use an extra qubit to encode. But what we are doing is put everything here, okay? So I don't do this. I don't know, I think maybe...
Okay, yeah, probably, yeah. Thank you.
That's all the time we have for questions, so let's thank our speaker again.